In this video, we're going to learn about exponential growth in word problems. So just to recall what exponential growth is, it's basically a function that's going to keep on increasing. So it's going to look something like this. So if this is the x-axis, y-axis, exponential growth means it's a function that's growing by a certain percent or a certain factor over a certain amount of time. So it's going to constantly increase. So when you're trying to identify if you have exponential growth, you're looking for words like increase or went up or appreciates by a certain percent, or maybe it doubled, it tripled, it's growing by a factor, something along those lines. So if we look at this opening exercise to try to understand what exponential growth is. So in 1985, there were 285 cell phone subscribers in East Rochester. The number of subscribers increased by 75%, so that right there indicates it's going to be exponential because it's 75% is the rate, but it's increasing, so that tells me exponential growth. How many cell phone subscribers were in East Rochester in 1988? So we want to figure out basically from 1985 to 1988, what's the growth? So initially in 1985 is when we're starting this, so that's when t equals 0. There were 285 cell phone subscribers. So this is when t equals 0. This is the initial. So let's go ahead and fill in this table. So this is going to be 285. Then each year is increasing by 75%. So what that means is I have to figure out what 75% of 285 is, and then I have to add it to the 285. So what I'm going to do off to the side here is take 75% of 285. So you can do that by multiplying. So remember, you're moving the decimal 2 places to the left, or you're dividing that percent by 100. And when you do this, you get 213.75. So let's just keep it at 213 because we don't quite have that next whole number, even though you would round the 3 up based on the 7. In this case, we don't have quite 214 cell phone subscribers. We only have 213.75, so we're going to round down and just say 213 because we don't quite have that whole number to round up. So that means if I want to find how many in basically 1986, 1 year after, I'm going to take this amount and I'm going to add it. So add that to this, and we end up with 498 subscribers. So then if you want to know the next year, well, it's going to be 75%. It's increasing by 75% on this year here, on this 498. So I'm going to take 498 and I'm going to multiply that by 75%. And for that one, I'm going to get 373.5. Again, I'm not going to round that up. I'm just going to leave it at 373 because you don't quite have that next subscriber. We're going to go ahead and we're going to add that. So this is the increase, the amount that it increased. So let's add that. So you get 871 for that. So after year 2, you get 871. So here's the initial, year 1, year 2, and then the last year you're going to do the same thing. So we're just going to have 871 times 75%, or 75% of 871 is going to be 653.25. Again, we're not going to round that up. We're just going to keep it at 653. And then go ahead and add that on. So plus 653. So we get 1,524 subscribers in 1988, 3 years after the initial. So that's basically what exponential growth is doing. It's taking the percent and it's adding it on to the original amount. So the difference between decay and growth is you're increasing that percent, where decay you are basically subtracting whatever that percentage is. When we did our decay model, when we did the table in the previous video, we kind of took a shortcut. So instead of, if you remember, I was talking about a car depreciating like 15%. So instead of finding 15% and subtracting that off, it's like what I would have done here. I found the percent and then I added it. We just said, okay, well, instead of depreciating 15%, that means there's going to be 85% of our original, um, or we have 85% of the original amount is going to equal the new amount. So with growth, it's a little bit different. If you want to figure out, well, what did I really do without having to actually figure out 75% and then add it, you could have multiplied by 1.75. And what that would do is it would take your previous amount and it would find the percentage and it would add on this 213. So I could have multiplied this by 1.75 every time and I would have gotten these values that are boxed in. So that kind of leads us to the formula, which is, so again, formulas are helpful because what if you had to do this for 50 years? You don't want to have to go through this whole process 49 times. So the formula, the first formula, the percent one, which would relate to this problem, instead of subtracting that rate, it's going to look very much the same as the decay formula, but instead of subtracting the rate, you're going to add that rate. So this is going to create that 1.75 in this case. So just like before, A is going to be that initial amount, the y-intercept. R is going to be the growth rate. And this is for percents. So this was going to be a percent, but you're going to write it as a decimal. And then T equals the time. So this is for growth, so you're adding. We also have when you have a factor, so like double, triple, something like that. This one is really easy to remember because it's exactly the same as the decay formula. So the only difference is when B, if it's growing, if you remember from the first day, growing means it's going to be greater than 1. Decaying means that the B value will be between 0 and 1. So same variables here. A is going to be the initial, and B is going to be the growth factor. And that'll be a number bigger than 1, and then T is going to equal the time. So these two formulas end up coming out to be the same thing, because if you think about this previous example, the percent was 0.7 or was 75%. When I write it as a decimal, 0.75. If I add 1 to that, it becomes 1.75. And if you remember what I said, you could have just multiplied these by 1.75 and you would have gotten the same answer, because 1.75 is really that growth factor. That's how much it's growing by, because you're taking the original, you're taking 75% of it, and you're adding it, that 75% onto the original, which is getting you the new value. So if we go to the next page here, let's look at some examples of how we can use the formulas, because the formulas are definitely going to be helpful. So let's go to the next page, and we have the same situation from the opening exercise, but instead of having this in a table format, we're going to use our formula and see how we can apply it to the same situation. So same scenario, we have in 1985, 285 cell phone subscribers. So this is going to be your initial. It's increasing by 75%, so that means the rate's going to be 0.75. And we're going to start with just writing our formula. So our formula is going to be f of t equals a times 1 plus r to the t, so it's a growth function. We're going to plug in our 285 for our initial. 1 plus the rate, 0.75, raised to the t. And then, like I said before, the only thing that you can do with these is actually add the inside. You can't ever combine this 285 because the 1.75 belongs to the exponent and the 285 doesn't. So this is as best as I can simplify it. If I just write it as 285 times 1.75 raised to the t. And again, we know that this must be a growth function because that b value, the factor is greater than 1. So here's your percentage formula, here's that factor formula. So in the end, they end up being the same formula. It's just this is the way to go from the percentage to the factor formula. So if we look at the next example, using our equation, we want to determine the number of cell phone subscribers in 1988. Well, we already did this, and we got an answer, so let's see if we get the same answer. We should, because otherwise this formula wouldn't be any good if it doesn't give us the right answer. But let's just double check. So the starting year was 1985, so you would want to figure out, well, how many years have passed? So we would do 1988 minus 1985, and you get 3 years. So that means that the time that passed is going to be 3, so you're going to plug 3 into your formula. So 285, 1.75 raised to the 3. So enter that into your calculator, and you should end up with 1,527 subscribers. So compare that to the table value. So 1527, if we go back, we got 1524. So we're not getting the exact same answer, but we're getting something in the ballpark of being correct. Now, think about why this could be. So hopefully you're thinking, okay, well, remember all these scenarios when I rounded the percentage? Well, that's where I'm getting the issue, is because I rounded all of these percents, so this is off a little bit, or my formula is off a little bit because of the rounding. So just be aware of that. In this case, we rounded every time, where your formula isn't going to round until the very end. So this is actually going to be the more accurate answer to use. So are they the same? I'm just going to say very similar, slightly different due to rounding. And the rounding was occurring in that table. So then if we use this formula for the next problem, we want to know how many cell phone subscribers in 2015. So that means we're going to take 2015, we're going to subtract 1985 because that was the starting to figure out how many years. So that means 30 years. So you definitely wouldn't want to do a table for this. So you're going to plug in 30. So 285, 1.75 raised to the 30. So I'm using, remember, this original formula from up top. And when you do that, so we get 5,571,681,990 subscribers. Now, I don't even think ER possibly even has that many people, but for the sake of the problem, this is the predicted value that would occur given the fact that it would be a 75% increase every year. So obviously there's going to be some constraints when this is a real life situation, because once you exceed the population, well, you can't keep adding 75% every year. So we're going to leave this as our answer, but it's not really a realistic number because you don't have that many people living in ER. And this problem's made up overall, so we don't really know that this 75% increase really did occur. So just kind of go with it for the sake of understanding the math behind it. So let's look at the next problem here. So we're just going to do some more practice problems like this. So this problem's talking about a flu that hits our school on Monday, hopefully not our school, with an initial number of 20 ill students coming to school. So we start with 20. The number of ill students increases by 25% every hour. That's kind of scary. Create a model for the Monday flu outbreak. So we're just writing a formula. We're not actually going to be plugging in. It just says write the formula. So let's think about what formula we're going to use. Since it's increasing by a percent, that means we're going to use this f of t equals a times 1 plus r to the t. Make sure you're doing plus r because it's a growth function because it says increases. So then we have an initial number of 20. So f of t equals 20. 1 plus our rate is going to be 0.25. So 1 plus 0.25 raised to the t. So there's our formula. I'm just going to go ahead and add those because you'll typically when you see a problem like this, those are going to be added. Like if it were a multiple choice question, they wouldn't leave it as 1 plus 0.25. They would actually add it. So I'm just going to write that. Because this way too, you see that it truly is an exponential growth function because that growth factor is greater than 1. So that's it for this one. That's all it wanted us to do. So let's go ahead. Before we move on, let t equal number of hours in this case. Because it's 25% per hour. So we should at least have what our variable represents in this situation. So then let's move on to the next example. So example 3. So again, we're talking about East Rochester. Don't believe this. It's not accurate. I mean, it could be accurate, but not that I know of. So this is talking about in 1995, there were 85 rabbits in East Rochester. The population increased by 12% each year. How many rabbits were in East Rochester in 2005? So we started with, initially we're talking 1995, our starting year. There's 85 rabbits. So this is our initial. Then it's increasing, so growth by 12%, so exponential growth. We want to know how many rabbits were in East Rochester in 2005, according to this scenario. So we're going to start with our formula for percent, a times 1 plus r to the t. We have a is going to be 85, that's our starting amount. 1 plus, so our rate is going to be 0.12. Remember, divide that by 100 or just move the decimal 2 places to the left. So our formula is 85, 1.12 raised to the t. So there's your formula. According to this situation, we want to know how many rabbits were in ER in 2005. So that means we're going to take 2005 and we're going to subtract off 1995 from it. So we get 10 years that we're looking at. So that means I'm going to plug 10 into my formula. So when you plug 10 in, we get 263 rabbits. And for this one, I rounded down again, even though, like, by rounding rules, 263.9971 is what I would have gotten out. That would have, by rounding rules, you would have rounded up. But based on the situation, 263.9 rabbits isn't quite 264, so you have to round down to say there's only 263 rabbits after 10 years. Maybe like 10.1 years would be 264, but we're just talking about after 10 years, so we have to just basically say 263. We can't say we get the next rabbit. So then I just have a couple more examples to do with you. So last page here. I want to at least show you one with a factor. So for this one, we're talking about bacteria. So one of the most common examples of exponential growth deals with bacteria. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. So I see the word doubling. That tells me an exponential growth. Because if it's doubling, it's going to be times 2. So if we start with only 1 bacteria, so there's our initial, which can double, so here's our rate, so our growth rate is going to be 2. It's going to double every hour. How many bacteria will we have at the end of 1 day? So the end of 1 day tells me that the time is 24 hours. Because it's talking about doubling every hour, you have to make sure that your time is in terms of hours. So our formula for this is going to be f of t. We're going to use the rate formula, a times b to the t. So f of t, our initial was 1. It's doubling. And then if we want to find after 24 hours, 1 day, so I'm going to go ahead and I'm going to plug in 24. So we have 1 times 2 raised to the 24. So for this one, we get 16,777,216 bacteria. Again, we're rounding down for any decimals. So in this case, it should just come out to be 16,777,216 bacteria. A lot of bacteria in 1 day. Now, this is more of a realistic problem. This is a true situation for this. So then the last one here, example 5, we are talking about a rare coin that's appreciating. So appreciate is another word that represents growth. So remember, depreciate meant decay. Appreciate means growth, and it's increasing at a percentage rate, so that tells me exponential growth. If the initial value of the coin is $500, so there's our initial, after how many years, so that means you're trying to find time, will its value cross the 3,000 mark? So basically we want to know, well, when will it at least be $3,000? So start with our formula. If it's growing with a percent, we're going to use a times 1 plus r to the t. We know some information right off the bat. Remember, this 2 decimal places is going to be 0.052. Make sure you're paying attention that it's moving 2 decimal places to the left, or just take 5.2 and divide it by 100. I know when they have decimals, the percents have decimals, you still got to create the percentage into a decimal by dividing by 100. So just make sure that your rate is 0.052. So I have my initial is going to be 500, 1 plus the rate, I'm going to keep t, and then I'm just going to combine my 1 and 0.052, so I get 1.052 to the t. So here's my formula to show the formula that will model the value of the coin after t years. So there's the formula. Now what we want to do is we want to actually answer this question. We want to know how many years will it take to cross the $3,000 mark. So that means $3,000 is the value, so that's going to be f of t. So we're going to plug in 3,000 over there, and we want to find the time. So that means I want to take this equation and I want to solve for t. And when you have an exponential equation like this, there's no way for you to solve this algebraically right now. You'll learn it later on in Algebra 2. It's not something that we do in this class, in this course. So it's not as simple as just dividing by t or dividing by the numbers in front of t, because t is an exponent, and you can't undo an exponent. You know how, like, if it's to the second or to the third, you take the square root or the cube root. There's no, like, tth root. So you have to, for this class, solve this graphically, and then eventually you'll learn how to solve these algebraically. So to solve this graphically, we're going to do what we did in the last lesson. We're going to set one side in our calculator in F1. Actually, before we do that, let's make it a little bit easier, because if I put this in right now in F1, F1 of X is going to be 3,000. That's going to be a massive number to try to look at on a graph. So to simplify this, what you can do is you can divide everything by 500, since you have a 500 in front. And what this will do is it'll cancel that out. So this side you'll just have 1.052 to the t. And on this side, you'll be left with 6, because you'll have 30 divided by 5. So now you have a much nicer equation to deal with. You're allowed to divide by 500 because it doesn't belong to that t. Just the 1.052 you can't divide out because that's being raised to the t power. So now that I have this more simplified version, now I can plug one side into F1 into your graph and then the other side into F2. So this will be one of them, this will be the other. So what you're going to end up getting is a picture that looks something like this. So I label my axes. So why don't you guys go ahead and type this into your calculator. So I have y equals 6 should be just a horizontal line through 6. So this is f1 of x equals 6. And then the other graph is going to be a growth. So it'll look something more like this. So this will be the second one. So your goal when you get this in your calculator is first of all to see that intersection. So to see that intersection, if you go to zoom standard first, you won't see the intersection, you'll see like this and this. So then what you can do is you can either hit control in like the center of your cursor there and move the graph, or you can just zoom out because you really need to be able to see this point on your graph, this intersection point. And then once you can see that intersection point, so you're just going to have to either move it or zoom out so that you can see it. Once you can see it, then you're going to do the menu, analyze graph, and then intersection. And then those little lines will show up, those dotted lines. And then remember, you have to select somewhere so that this point is in between those two lines, and then your calculator will tell you that solution. So that solution that you should end up getting is 35.3 comma 6. So the solution is 35.3 comma 6. So let's just interpret what that means. So this value right here is the t value. So this is the time in years. That's t. And then the 6 represents the y value. So this represents the amount of money. So this is the value of the coin. So to answer the question, it says, after how many years will its value cross the $3,000 mark? Well, after 35.3 years, so basically you would just say after 35 years. So after 35 years. Now remember, we don't see 3,000 here because we divided by that 500. The solution is still going to be the same. It's just you're not seeing it in the graph because we divided both sides by that 500. But if you plug in the 35 in for t into your original equation with the 500 being there, you're going to see that this will satisfy crossing that $3,000 mark.